Hello everybody, welcome back to yet another organ system that deals with the movement of molecules in a body. We have seen the respiratory system, moving carbon dioxide and oxygen in and out of the blood. Here is a little remnant of the digestive system where we have seen absorption from the small intestine responsible for the movement of glucose, amino acid, triglycerides into the blood with the purpose of supplying individual cells with those organics. In chapter 25, we have seen the four parts to the ATP production, and we have seen that all these three organic nutrients can provide ATP, can be plugged into those four processes. What we have already seen in the digestive system that toxic waste products are produced by these cells. We have seen ammonia production, especially by the liver. The liver also takes some of the ammonia and converts it into urea. And then in that electron transport chain portion of the ATP production, we have seen huge amount of hydrogen ions made. This is the byproduct of the catabolic reaction, whether you are degrading glucose, amino acids, or the fatty acid or glycerol portion of triglycerides. It all goes to eventually the electron transport chain where hydrogen ions are released from those carriers. Because ATP production must go on 24/7, normal consequence of that is that hydrogen ion production must go on as a waste product production. So what happens to all these surplus hydrogen ions? Cells will release them into the interstitial fluid, and just by plain diffusion, large concentrations of hydrogen ions will move into the bloodstream. Same is true for ammonium ions or urea. And so what we see, normal consequence of living, producing ATP, that there's an accumulation of all these waste products in the blood. As it turns out, ammonium ions and hydrogen ions can be toxic to cells. Hydrogen ions are especially dangerous, and we'll be seeing in the next chapter that our blood pH, the concentration of hydrogen ions, is kept in a very, very narrow homeostatic range. So our body pays exquisite attention to how much hydrogen ion we have. It means, though, that if we have a limited tolerance for hydrogen ions in the blood, that homeostatic pH range, we have to do something with this huge tsunami of hydrogen ions. And here comes to the rescue the urinary system. So in yellow arrows is the very, very sketchy summary of the urinary system. The urinary system will provide for the removal of hydrogen ions, ammonium ions, urea, and open up a waste product stream, which is the urine stream. And we will be, thanks to these workhorses, the nephrons in our kidneys, will be able to remove hydrogen ions, ammonium ions, urea, waste products, and many other things, and move it outside the body through the formation of the urine stream. So the story of the urinary system is how we take from blood these waste products and move them into a new product stream, a urine stream. As we'll see that this is happening by microscopic workhorses, the nephrons, we'll say very, very little about the gross anatomy of the kidney, We'll spend most of the time, even in this first part of the urinary system lecture, in the world of the nephrons. And so let's take a look first as a bird's eye view of the urinary system, and then very quickly we'll be focusing on those structures, the nephrons, and how they make urine, how they remove waste products from blood. Just one more aspect of the mandatory nature of waste product removal is that in chronic kidney failure, when there is no urine production, all these waste products end up bottled up in the blood. The chronic kidney disorder, kidney failure, will give us a lifespan of 10 to 14 days. When dialysis no longer works, the only hope for those patients is a kidney transplant. And every year, thousands of patients are dying waiting for kidney transplant. So the accumulation of these waste products can be deadly in our body. So we do have a mandatory way to remove these waste products. This illustration is very similar to what you might remember seeing on a minute or so. Urinary system from a gross anatomical point of view is tremendously simple, nothing like what we saw in the digestive system. We have kidneys where urine production occurs. We have ureters to take the formed urine to the storage place, the bladder, and from bladder we have urethra to move the urine outside of the body. We're going to spend a huge amount of time here in the kidneys. At the very end of the second part of this lecture, we'll briefly mention the ureter, bladder, and the urethra. So kidney functions, at the very bottom, you see the excretion or removal of wastes and foreign substances. Foreign substances could be anything that we take. Consider medications, for example. They are foreign substances. They are not serving our purposes as energy production or building blocks to build proteins, let's say. They are all removed from our body. We mentioned earlier kidney functions such as erythropoietin production, vitamin D production. We're not going to go back to that and rehash that. And in the next chapter, we'll say a tremendous amount about the regulatory functions. Understanding how the nephron works will be tremendously helpful in the next chapter, where we look at pure physiology, how blood electrolytes, how blood pH, how blood volume is regulated. So we are going to focus mostly on the removal of waste products in this chapter, and again in the next chapter we'll expand on the regulatory aspects of the kidneys. So external anatomy is a large bean-shaped organ. This word retroperitoneal is explained best on the next slide. So here's a transverse section where you can see the two kidneys. And retroperitoneal means that the kidneys are behind the peritoneum, the parietal peritoneum. So here is the line of the peritoneum, a little darker black here, and the kidneys are behind, posterior to it. What holds the kidneys in place is these adipose capsule and renal fascia. In the digestive system, we have seen many folds of the peritoneal membrane anchoring the stomach, liver, small, large intestine. None of this is helping here. Our kidneys are kind of pushed against the backside of the abdominal cavity, mostly by this renal fascia. It's a saran wrap thin connective tissue that kind of pushes the kidneys against the posterior wall of the abdominal cavity. If we cut a kidney open, we'll see three different looking areas. So these are the regions of the kidney. On the very outside, we see a lighter colored region. This is the renal cortex, and we'll come back to this a number of times when we talk about the nephron, just how urine production works. Many important players, parts of urine production is found in the cortex. There is a darker, more central region, the medulla. If you take a closer look, the medulla is made up of several pyramid-shaped or triangle-shaped structures. Their name is pyramid, and this is where the last stages of urine production will occur. And the third region is the renal sinus. On this artistic rendition, it's this gray area. We have calyces to collect urine from the end of the pyramids, and urine is channeled into the renal pelvis and into the ureter. So in terms of urine production, renal cortex and renal medulla will garner our attention. We're not going to say any more about the renal sinus. Another aspect of kidneys that we have to mention, blood supply, because we have to remove those waste products from blood. No surprise that huge proportion of our cardiac output is pumped through the kidneys. We need to maintain this to remove sufficient amount of waste products. As you'll see, waste products will be removed from the arterial blood, so renal arteries bringing large amount of blood to the kidneys are essential to remove that sufficient amount of waste product. Another aspect of gross anatomy, and we'll see the role for it at the end, towards the end of today's lecture, a nervous system. Sympathetic division of the autonomic nervous system regulates blood flow, and we will be looking at this once we find the blood source for the urine production. We need to get close to the nephron to see that the sympathetic division of our autonomic nervous system will not be acting on the renal artery, but deep in the tinier blood vessels in the kidney. So here's that magic workhorse, working unit, many names for it, of the kidney, and this is called a nephron. In this first sketch of the nephron, and we might see this a little more. Here is the blood source that will be used to remove waste products, and if you can recall the two processes we've seen in the chapter where we saw capillaries leaking fluid. This is where fluid will be leaking from these capillaries. This portion of the nephron is called a renal corpuscle, and we have filtration, very similar to what we've seen in the hemodynamics chapter. And then the filtered liquid will go through processing. The name of this processing is reabsorption, and reabsorption removes useful material from this forming urine and returns it into the blood. Eventually, at the end of this set of processes, urine will be leaving at the end of the pyramids, at the papilla of the pyramid, in form of dilute urine. We'll come back to this a great deal. We'll talk about the numbers as well. This is just a basic introduction to this workhorse of our kidneys. Especially chapter 17, we will reiterate, and maybe the end of the second part of this lecture, the role of the juxtamedullary nephrons. When we are dehydrated, our nephrons carry out especially important function of fluid, water preservation, and the juxtamedullary nephrons are a lot more useful for that purpose. Most of our nephrons are cortical nephrons. This is the type of nephron that carries out most of that waste product removal. In terms of histology, the renal corpuscle is made up mostly of simple squamous epithelium. Here is the blood vessels. These are capillaries, so looking back into the blood vessel chapter, no surprise that these capillaries are made up of simple squamous epithelium. These loops of blood vessels are called glomerulus. And so this is the glomerulus we'll be talking about in a half hour or so, glomerular filtration rate. So these capillaries, again, the wall is made up of simple squamous epithelium. When we look at the tubular portion of the nephron, whether it's the proximal convoluted tubule, loop of Henle, distal convoluted tubule, collecting ducts, we see simple cuboidal epithelium. A lot of the times we see microvilli, especially in the proximal convoluted tubule. There's a lot of transport, fluid transport and material transport will happen through these cells. We'll detail those processes in the second part of this lecture. So all in all, it's a very, very simple structure. You don't see smooth muscle inside here. You don't see a connective tissue support like cartilage or bone. Very simple epithelial set of structures, surprisingly life-maintaining and tremendously sophisticated, as you'll see through this chapter and also in the next chapter as well. And we are pretty much done with gross and microscopic anatomy. Here is what we can say about the outline of the physiology. So physiology is nothing else but urine production. Urine production is nothing else but opening a waste product stream. And so here in the renal corpuscle, through the capillaries of the glomerulus, here's this process, filtration, again very similar to what we've seen in normal capillary bed. Fluid, plasma fluid will be squeezed out of the blood vessel through the blood vessel walls, and that is the process of filtration. The filtrate will be processed in the tubular portion, the proximal convoluted tubule, loop of Henle, and the distal convoluted tubule, and in the collecting ducts. So here we see the reabsorption, again very similar to the similar idea to the capillary bed. Movement of molecules will be going from the filtrate back into the blood. We also see in some parts of the tubular portion of a nephron secretion. dumping more waste products, a lot of the times hydrogen ions. We'll be seeing that again in the second part of this lecture. Today we'll be focusing on the glomerular filtration function and regulation of the renal corpuscle. So filtration is filtration is a process where a driving force squeezes plasma through the wall of this blood vessel. In the case of the glomerular capillaries, this is a little more sophisticated. So here is the magnified filtration membrane. Inside this glomerular capillary, blood is flowing. Here we see the basement membrane. In yellow we are seeing the endothelial cells themselves. These openings are the fenestrations, and the fenestrations have small enough openings that red blood cells, white blood cells, and platelets cannot pass through. So what's passing through here is just the plasma. The plasma will also be filtered by the next layer, which is this grayish layer, the basement membrane underneath the endothelial cells. Large plasma proteins will be stopped here. What are large plasma proteins? Think about HDL, LDL, lipoproteins, chylomicrons, clotting proteins, antibodies from our immune system, albumin. They are all retained in the blood. They cannot pass through here. And then the third part of this filter comes from this unusual looking cell sitting outside the blood vessel, and these slits, these openings, form the last layer. Even medium-sized proteins are stopped from passing through here. So most of the hormones will be, protein hormones will be stopped. Insulin, for example, will be stopped here. Small protein fragments can pass through, and many urine analytical procedures are establishing diagnosis based on the proteins that pass through this filtration membrane. So this is where we are removing waste products. The waste products are much smaller than even the smallest proteins. So waste products are streaming through here. So in terms of the speed of this filtration, we are filtering 48 gallons per day. This is the amount of filter that's produced here. And so we have little resistance from a membrane, huge surface area because of these many loops, and having a million nephrons in our kidneys. And also the driving force will also help push plasma fluids through the walls of these blood vessels. So in terms of the driving forces, the net filtration pressure is relatively small, 10 millimeters of mercury. However, this is coming from the overwhelming value of blood hydrostatic pressure or blood pressure. So we have seen blood hydrostatic pressure driving filtration in a regular capillary bed. This is the major driving force. The opposing forces are not large enough under normal conditions. If our systolic blood pressure drops below 45 or 50, filtration will stop or slow down tremendously in the kidneys. So continuous low blood pressure will slow down waste product removal. Under normal conditions, the net filtration pressure is coming from the large value of blood hydrostatic pressure overwhelming the capsular hydrostatic pressure, which is the pressure of fluids pushing back against the filtration. And we also have colloid osmotic pressure, water wanting to go back into the capillaries, but those two forces are overridden by the blood pressure. So we said with great certainty that our filtration rate is 48 gallons per day. So here is the per minute rate. And if you pick up a water bottle, that's about 500 milliliters. So every 5 minutes, our kidneys are making more filtrate than fits into a regular water bottle. And here is one other kicker, if you're not impressed by this volume, that we have to keep this filtration rate steady. So why is that? If the filtration rate is too low, we are not removing enough waste products. It's kind of weird that our health, the removal of waste products, is dependent on this huge filtration rate, but that is true. We also don't want to increase the glomerular filtration rate too high. Now, why could that be harmful? Shouldn't we be better off removing more waste products with an even higher than normal glomerular filtration rate? This is related to the reabsorption part. See, once we are creating this fluid, the filtrate, right, it contains waste products, but it also contains small nutrient molecules. Think about glucose. Glucose is much smaller than a protein. It will be in this filtrate. Think about all the amino acids. They will be in this filtrate. Think about electrolyte. Our blood needs proper calcium, sodium, potassium levels. Yet we are removing this at a breakneck pace here into the filtrate. So we are losing these useful substances with every milliliter or gallon of filtrate. So if our filtration rate is too high, we will not be able to reclaim these substances in the rest of the nephron. So we have to keep this glomerular filtration rate steady. And so the last part of this lecture is approaches by the body of how to do this, how to keep glomerular filtration rate steady. And you're saying, okay, so why would glomerular filtration rate change in the first place? So here comes the link to the main driving force, blood pressure. So the net filtration pressure affects glomerular filtration rate, and without these regulatory mechanisms that we'll talk in a few minutes, an increase in blood pressure will increase glomerular filtration rate proportionally. So with these processes, with these regulatory steps, we achieve that our blood pressure can go up to 180 millimeters of mercury systolic pressure. We can still maintain a steady glomerular filtration rate. Without those protective measures, without those regulatory measures, if we are exercising, if we are put into fight or flight response, If our blood pressure is high naturally, we're suffering from hypertension, our glomerular filtration rate will exceed normal, and there are many deleterious consequences that can come about as a consequence of that. So thanks to all these measures that we will talk about, we can go into fight or flight response mode, we can go and exercise, and our glomerular filtration rate will still remain steady. So here is the first regulation of the filtration rate, and this is built in to the nephron. This is called the auto regulation. I'm going to switch to an image, but we'll talk about the myogenic mechanism and the tubuloglomerular feedback. These sound weird. I'll explain all these terms. So here we are looking at the renal corpuscle. Atrionatriuretic peptide has the goal and the effect of increasing glomerular filtration rate. So atrionatriuretic peptide, or ANP, is produced, if you remember, by the atria when they are overstretched, and it means we have way too high blood volume. How to normalize that blood volume? We're going to allow surplus plasma fluids to be filtered through the glomerulus. This is a very different mechanism. The afferent arteriole won't come into effect here, but if you look at these yellow patches of cells, when these cells shrink under the effect of ANP, a smaller yellow patch will allow larger surface of the glomerulus to filter, and a shrinking of these mesangial cell patches will lead to increased glomerular filtration rate. This is temporary. As soon as blood volume is reduced, ANP is no longer produced, but with ANP present in the blood, these glomerulus loops of glomerulus will produce much higher glomerular filtration rate. This is an emergency situation. We cannot stress our atria, so we have to get rid of surplus blood fluids, and the way to do this is ANP forcing the glomeruli to filter more, and that happens by the shrinking of the mesangial cells, getting out of the way of filtration here in the glomerular corpuscle. I'm sorry, in the renal corpuscle. I'm not going to say more about this slide. Again, we are going to have to vasoconstrict afferent arteriole. When you look at whether moderate or extreme, the common denominator is vasoconstriction of afferent arterioles. And so here's the last way to moderate or regulate glomerular filtration rate. Again, we want to keep this steady. And this is the role of the endocrine system hormones. So let's take a look at angiotensin. When we have high blood pressure caused by the renin, angiotensin, aldosterone system, high levels of angiotensin is present in the blood. We looked at angiotensin in the blood vessel chapter as a hormone that increases blood pressure. So yet again, the challenge is increased blood pressure in the body now from the presence of angiotensin. How can we possibly counteract that at the glomerulus or the renal corpuscle. Yet again, vasoconstriction will be caused of the afferent and efferent arterioles. Again, this is a steady recurring theme. The afferent arterioles undergo vasoconstriction. Again, we'll be cutting, excuse me, cutting the blood flow to the glomerulus. These smooth muscle cells have angiotensin receptors, and those smooth muscle cells can respond to high angiotensin levels by going into vasoconstriction. If you remember way back in the blood pressure chapter, we have seen one outlier hormone, and that was atrionatriuretic peptide. This is an outlier here too, and I'm going to go back to the slide of the renal corpuscle and explain atrionatriuretic peptide there.